this lesson, we're going to talk about the binomial theorem. We're going to use the binomial theorem to expand binomial polynomials of the form x plus y to the power of n, where n is a positive integer. In the expansion of a binomial polynomial of this form, you are going to find n plus 1 terms, so one more than the degree of the polynomial, and each of the terms is going to have the form an x to the power of n minus r y power r, where an is going to be the binomial coefficient and n minus r and r represent the powers of the two variables x and y. In the expansion of the binomial polynomial, the powers of x, the first term in the binomial, are going to decrease as we progress in terms in the polynomial, while the powers of y will increase. So x will start with the first power equal to n and will end in the last term with a power of 0, while y starts with a power of 0 and then it will increase by 1 in each term until the last term of the expansion will have a power of n. Additionally, for each term in the expansion, the power of x and the power of y must add to n. With that said, we can state the binomial theorem. The binomial theorem says that the positive integer power of a binomial can be written as an expansion of n plus 1 terms, where each of the terms is represented by this general form, where CNR or AN, as before, is the binomial coefficient, and x and y are a combination of powers of x and of y that add up to the power of n. So though this is a polynomial, not all polynomials are going to be binomial polynomials. Only polynomials that satisfy these conditions are called binomial polynomials. Now, in order to put this into practice and take some binomials and find their expansions, we need to understand what the binomial coefficients are going to be. So let's talk about binomial coefficients next. To start, let's consider the expansions of a few binomials. The first binomial that we have is x plus y to the power of 0. Now we know that that expansion is equal to 1, because anything to the power of 0 is going to be 1. Next, we have x plus 1 to the power of 1, which is x plus y, because anything to the power of y is the same object. Now, x plus y to the power of 2, we are more familiar with that one from the time when we learned factorization. X plus y squared is a perfect square, and the expansion of the perfect square is x squared plus 2xy plus y squared. Now, if we keep multiplying the previous expansion by x plus y, we would get our next expansion, x plus y to the power of 3. This expansion is also familiar to us from the time of factorization. The expansion would be x power 3 plus 3 times x power 2 y plus 3 times x y power 2 plus y power 3. And if we continue expanding the polynomials, x plus y power 4, x plus y power 5, and so on, we will get these expansions. Now let's take a look at the coefficients of these expansions. The first expansion, x plus y power 0, was 1. There's only one coefficient. However, in the expansion of x plus y to the power of 1, there are two coefficients, the coefficient of x and the coefficient of y. They are both 1. So let's make note of those two coefficients. For the expansion of the squared, we get the coefficients are 1, 2, and 1. Let's write those coefficients right below the coefficients of the previous expansion. And let's do the same for the expansions for x plus y power 3, x plus y power 4, and x plus y power 5. What we have built with the coefficients of these polynomials is what we call Pascal's triangle. This way we can say that the coefficients in a binomial expansion correspond to numbers in Pascal's triangle. Now we recognize in the triangle that there are a number of rows that we start counting from 0, 1, 2, 3, 4, 5, etc. that correspond to the power of the binomial. And also each coefficient is taking a place in the row. So for example, the coefficient in the expansion of x plus y power 3 that is in the second position, that is going to be 3, is taking the second position of the fourth row. Now each row starts counting from 0, and each element in the row also starts counting from 0. You can think of the power r as corresponding to the exponent of the corresponding power of y. And this is because the powers of y are going to have exactly these same values. They are going to be increasing starting from 0, and they are going to end matching the value of n. There are many relationships between the coefficients in Pascal's triangle, and they are left for you to explore at your own time. And if you're interested, you are going to be surprised by how dynamic these numbers can be. They have a particular relation with Fibonacci sequences that you can explore and look a little bit more deeper. But for the time being, we are going to go ahead and give a definition for these coefficients. We will define a binomial coefficient as the coefficient c and r such that the top is n factorial divided by r factorial times n minus r factorial. At this point, I hope you are familiar with the definition of factorial. N factorial is defined as the product of the natural numbers from 1 to n. Now there is another interpretation to this coefficient. So when we touch on the topic of combinations and permutations, we are going to be able to understand the connection between the Pascal's coefficients or binomial coefficients and combinations. So let's go ahead and move on to using the binomial theorem to find expansions of binomials. For our first example, we are given the in our first example, we are asked to expand the binomial 2x plus 1 to the power of 4 in In our first example, we are asked to expand the binomial 2x plus 1 to the power of 4 in descending powers of x, simplifying our answer. Because this power is very, very small, it's 4, we can use the Pascal's triangle instead of using the general formula for the binomial theorem. So for power 4, we know that the triangle is in the stage 1, 4, 6, 4, 1. So these are going to be the coefficients of the polynomial that I have. Now, what does that mean? That means that the polynomial 2x plus 1 to the power of 4 is going to be 2x starting at the power of 4. And from here onwards, for the next terms, it's going to decrease by 1 each time. Then the second term is going to start with a coefficient of 4. The power of 2x is going to be 3, and 1 is going to start appearing with the power of 1. Now the third term is going to be coefficient 6, 2x to the power of 2, because we are decreasing the powers of 2x, and 1 would appear with a power of 2. Plus, the next term would start with a 4 coefficient, 2x to the power of 1 times 1 to the power of 3, and we would end with a 1 as coefficient times 1 to the power of 4. So simplifying, 2x plus 1 to the power of 4 would be equal to 16x power 4 plus 32x power 3 plus 24x power 2 plus 8x plus 1. For our second example, we have the expansion of x plus 2 to the power of 5. We are asked to write down the number of terms in the expansion and to find the term in x power 3. So as you can see, this question, they are not asking us to do the full expansion. So we should avoid doing the full expansion. However, we do want to find a specific coefficient because we need to find a specific term. So in that case, to do B and find the coefficient for x power 3, we are going to use the general term of the binomial expansion. Now for A, we said that polynomials are going to have n plus 1 terms. So since this polynomial has a degree of 5, or the highest power that we're going to get is 5, then we can say that this polynomial has 6 terms. There's no need to do the expansion. Just remember that the number of terms is given by the exponent plus 1. For B, we are going to use the general term C and R, x to the power of n minus r times y to the power of r. In this case, we are identifying that n is 5 because that is the maximum power of the polynomial. So our coefficients are going to be C5r. We need x to be to the power of 3, and y in this case is going to be substituted with 2. So substituting 2, I get 2 power r. Now what I need to know is what should be the value of r. Now we stated that in binomial polynomials, the powers or the exponents of the two terms in the binomial, in this case the exponent of 3 and the exponent of 2, need to add up to the total power. So in this case, 3 plus r needs to add up to 5. That way I know that r is going to be 5 minus 3, r is equal to 2. So now that I know r, I can substitute C5, 2, x to the power of 3, 2 to the power of 2. Now let's calculate what the coefficient C52 is. We could use Pascal's triangle, but we're going to use the general definition. So C52 is 5 factorial divided by 2 factorial times 5 minus 2 factorial. That is 5 factorial divided by 2 factorial times 3 factorial. And remember that factorial is the product of all the natural numbers up to the given number. So 5 factorial is going to be 1 times 2 times 3 times 4 times 5. And 2 factorial is 1 times 2. And 3 factorial is 1 times 2 times 3. So we can cancel 3 factorial and we can simplify 4 with the 2. And we get that the coefficient C25 is equal to 10. Now for the final answer, we need the term in x power 3 is given by 10 x power 3 times 2 power 2. That is 40 x power 3. This would be the final answer. To finish, let's do example number 3. The third term in the expansion of x plus p power 8 is 252 x power 6. Find the possible values of p. In this problem, the maximum power, n, is going to be 8. And since we are given the information for one term of the expansion, we need to work with the definition of each term. So what I'm going to do is I'm going to create the equation C n r x to the power of n minus r y to the power of r. This should be equal to 252 x power 6. And now what I'm going to do is I'm going to substitute y with p and n with 8. So I get C8r x power, I know that the power of x that I want is 6, and y I'm substituting it with p. So p to the power of r should be equal to 252 x power 6. I know that the exponents of x and of p should add up to 8. So 6 plus r should be equal to 8. That means r is equal to 2. That way I can continue to substitute once again, and I get C2 8 x power 6 p power 2 is equal to 252 x power 6. At this point, I would like to cancel or simplify x power 6, and also I would like to substitute what the binomial coefficient is going to be. Using the definition of the binomial coefficient, C8 is 8 factorial divided by 2 factorial, 8 minus 2 factorial, times p squared equals to 252. Now this is the same as 8 factorial divided by 2 factorial times 6 factorial, and everything else remains the same. Now I could substitute 8 factorial. I could write it as 6 factorial times 7 times 8 to help me in the calculation and to make sure nothing is too long to write. And I can cancel the 6 factorial in the numerator with the one in the denominator, and then I can simplify 8 with 2 from the factorial in the denominator. From here we have 7 times 4 p squared equals 252, or p squared equals 252 divided by 28. That means p squared is equal to 9, and that gives an answer p equal to plus or minus the square root of 9. So p is plus or minus 3.